So now it's time to pick things apart. Basically, we've built all the stuff. Let me quickly start the notebook. It's in projects, it's in circ, and I think it's just in notebook, Jupyter notebook. Jupyter notebook. That's one thing. Then to the Ising model that we want to have for sure as well in here. Ising model. Exactly. So basically what I want to try to understand, right, is I want to try to understand how each of the bits and pieces of the circuit really relate to the actual problem shape, right? Because we said the first layer of X rotations is to get you into superposition of all the possible inputs. Then you've got the Z operations, which basically what they do is it's to reflect the H field, so the external field. The control Z to reflect. I think it was positive ferromagnetic, and then so the Z is for the +1, and then the for the -1 it's something like this. So here you've got, for example, let me find an example that's clear to see. Down here, there's a better example. So here you've got one example where you've got like these two qubits that have an X and an X gate, then a control Z, and then an X and an X gate again. And that's what I wanted to basically do today, and then even maybe try to change. So this is this. So here we've got the problem, because I was wondering whether for the Z layer one step, the X layer, that's what I'm looking for, the rotation X layer. Oh, here. So I wonder whether I could not just put here an X gate and a Hadamard gate without any, you know, without the parameter actually making any, and see how that would change. But let's do this as a second step. First step is like, let's try to break this down using Quirk. So how are we gonna do this? Basically, what was here about ferromagnetic? So if the J value is positive, is considered an attraction to ferromagnetic. If it's, so I guess that the kind of attraction. Okay, so if it's negative, it's considered antiferromagnetic. So in a ferromagnetic Ising model, spins desired to be aligned. The configurations in which adjacent spins are of the same sign have higher probability. In the spins desired to be aligned. The configurations in which adjacent spins are of the same sign, they have higher probability. Okay, in a ferromagnetic model, adjacent spins tend to have opposite signs. In an antiferromagnetic model, okay. The sign conversion also explains how a spin side J interacts with an external field, namely the spin side wants to line up with the external field. Yeah, so that's how they interact with the external field. So if the H is positive, then it desires to line up on the positive direction. If it's negative, in the negative direction. Okay, that should give us some clue of what to expect. But basically, so what we got here, right? What we've got here is the first step is getting us into superposition. So let's we'll do a simplify. We'll do something like with just with 4 qubits. We'll do, and I guess this is a. So I'm considering to use the dynamic gates to see the effect. I think that can probably be an interesting, because I could easily just say could just say, for example, it's an X gate, and we're not gonna make it dependent on T. We're gonna just say, I don't know if that, so this is just a. So we can probably do two versions. Can I just copy that? Because I'm not having a mouse, so so 0.1. That 0.1 is probably not the gets exponent 0.1. I'm not sure if it's the same equivalently to the cert, like in terms of how they use it, but basically, let's see. So what does this give us? It's sort of, as you can see, it's like a superposition of possible states, but it's just, yeah, you can probably change some of those things in here, and then you're kind of filling those up a little bit more. So this is one thing, and then it also changes. It's interesting to see. It also changes the phases. I wonder how the Hadamard will work here. Because basically, if I now have a chance display, separately, and that's kind of what matters. Despite the fact that overall at a state level, and I think in this case we don't care, we care about the individual qubits, so that's kind of what matters in this case. It's like, so with this rotation we get a 2.4% chance of this being a 1 and the rest being 0, right? So okay. Now we go ahead and based on this on the H field, right? We are putting these Z rotations. So in this case, that's these here, which basically phases. It basically phases the. It's this here. Interesting. So, but as you can see, that doesn't change your probabilities. So that's what's a bit confusing me at the moment. We'll fix it. We'll just do this. I'm not doing any particular. I mean, I was just now doing that, but I'm not doing any particular. It's not that I'm doing, but we can try to do that particular configuration in here. But I wanted to try to understand first, just with those 4 qubits. Maybe I should do 2 qubits, and then I should try to understand. It doesn't matter. Let's keep. So, what if we now do a what if we now do a control Z, parametrized, right? So, for example, let's say between this qubit and this qubit, and this is going to be 0.3. Interesting. It's interesting because it doesn't seem to change the probabilities of each separate qubit. And at the end of the day, as I've seen in this problem, that's what you What if I add the X gates around it? So we assume it's an antiferromagnetic. There's an antiferromagnetic influence. Oh yeah, oh yeah, oh yeah. That does change. Yeah, okay, but this will make it go back. Yeah. Nothing changes. Nothing changes. Nothing changes. And if I take a look at the amplitude display here, so you can see the changes are basically on from a phase perspective. But wait a second. There's one thing that there's one detail here. What is M? Why is there a key called X? Oh, maybe this is just where this is going to be put in in the results object. Parameterizing. Because for a second I thought maybe that's a key X. Okay. That's just a reference. Okay. No, because for a second I was thinking maybe that's some kind of like measurement on the x-axis or something. Interesting. If then let's say there's a control Z here, just for the sake of just for the sake of the example. What if I would change those things to be okay? That's what I should do is I should put them here and then see if that's different than after the circuit. So what if I would change those for simply come on, simply rising X gates. I think it doesn't. Those probabilities just grow together. It just doesn't seem like this is influencing anyhow. Okay, but then now I'm lost. Now I'm pretty lost. How is this then supposed to work? I mean, if those things are just, I mean, I'm assuming the X pow is an X gate rotation, right? And the Z pow is Z rotation. And then the other thing is a control Z. That's what I'm... Where is this defined? Here, here, here. Control Z, pow gain. Those operations effectively only touch the the phases that you can see in the diagrams. I mean, I'm so it it does change the distribution of what's the final state you measure. What is the most probable state that you measure? And maybe that's the point. Probably. Because you're measuring all of them at the same time. So I was just talking BS when I was saying, no, you care only about, you measure each of them. I mean, you do a measurement, but you obviously can see the amplitudes changing in here, right? Slightly, right? So, but if you now turn those things, yeah, okay, the question is whether they're changing just because of these. That's the other. That's the other possibility. Because let's say we use these X rotations. Yeah, the amplitudes don't change at all. So you've got literally the same chance to measure each of. Doesn't make any sense. But maybe that's particular. Maybe it's because of that particular. So if I would now change those for. Oh, for the Z gates, you can only see the amplitudes are the phases are being same here. The amplitudes are not changing. So you literally have got the same chance of measuring any. Like, how is that? How is that useful as a model? I thought I got it, but now I'm more confused. Unless this measurement is a measurement on the X basis, which is then, because then what this would mean is that you would put a bunch of Hadamarts in here. And that basically changes the amplitudes, right? So you would have, sorry, I'm gonna fix that because otherwise it's confusing. So because I want to basically know whether how that portion affects the final outcome. That definitely changes the different measurements, but just because we're doing a measurement, just because we're applying a Hadamard, which it's not obvious from the circuit, I would should say. I don't think that's what's happening. Hmm. Now I'm totally lost. You know what I mean? I mean, it seems that the only things that influence those probabilities of measuring different things here and there, um, are the initial gates, the X rotations, which makes absolutely no sense. What for we're doing the whole thing in here then, you know? Um, oh, I don't know. I don't know. That sucks. There's nothing else about it. There's just I'm really lost right now. Gates, X1 gates, H gate. C naught. Let's control that gate. Oh wait a second. Oh no, phased X power gate. That's something else. X pow. I so uh, I would like to know what the okay something is not then I'm not using again the right I might not be using the right gates in here. That's the gate is equivalent to the circuit. P is the phase exponent. T is the exponent. No. Circ Z, circ RZ. Rotations about the Pauli Z axis. The matrix of this is this. But this is not Z pow. Mm, mm, mm. How do I know which gates to use? How do I know which gates to use for uh, what's the X pow? I mean, come on. It says rotation about X. This is the gate. Okay, so this is the gate, this gate. Google X pow gate. It's a gate that rotates around the x-axis of the block sphere. Okay. No, yeah, but then that's the right way. No, yeah, then this should be correct. X power gate, and the Z power gate is around the Z axis of the blocks here. Okay. The unitary matrix is these, and then G is the exponent. Okay. And for the X power gate, it's these in here. Yeah. I think. Hmm. I think they're the right ones, but then I just. Then that's not going to be the last video about it, I guess. Hmm. That's confusing. I'll have to leave it here. That I was not expecting that. I thought that would be easy to reason about. I mean, it's just either I'm using the wrong gates, or I'm missing something here, but I don't see the amplitudes changing. So what's the point in that? You know, I can as well just um, get rid of all that, because if I only care about the measurements, then that's about it. I mean, yeah. As I said, unless it's a measurement on the x basis, I can't. But I think this x, this is just a key, right? So this is just labeling, right? So you know which things to print in a histogram and stuff like that. What if I just Google Ising model quantum ansatz? So there is, of course, this in here, spin model, quantum phase diagram. That's Hamiltonian. Da, 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 da. Start off with the Ising model. Maybe I'll just ask here as well. Then notice that it's generated by the Pauli-Z operator. It's equivalent to an operator generated by single rotations. The idea is that the answer corresponds to applying the pulse generated by the term on the right hand side. Yeah, whatever. Change the Z power gate to an X power gate and got radically different results for the minimized energy. Yeah, maybe that's. I was wondering how exactly was the answers arrived at. Okay. So what I probably should do in the next video, maybe I'll try to play with the actual. So I've done this, then with the actual code. Where is it? I lost the here. Try to use other gates. Try to change those things. I don't know. Why is that even having any impact on the circuit? I mean, you can see this here, right? It's just. Maybe I should build exactly this one here, but if that's... Things don't change at all. I mean, we're just rotating. Yeah. Hmm. That's confusing. I have to rethink about it. Kind of think about it more. Do another iteration of this. Maybe I'll try to... What I can do is I can try to replicate exactly this circuit, and yeah, it's... I quite don't get it. I genuinely don't get it. These, and then, just like these, and this is maybe 0.2. I don't know. And then this is a control. It's just all... 0.2 times t, sorry. Or just t. Just t. Nothing. Just t. Just t. The amplitudes don't change absolutely. Because we're just rotating along the z-axis. Come on. I don't know. Good, I'll finish here. Hopefully I'll figure it out soon. Not good. Not good.